Welcome back to the second episode of this series about machine learning. In the last episode, we derived gradient descent and ascent in an intuitive way. Today we will implement these two algorithms in Python and dive a little bit deeper into how gradient descent and ascent work. You might ask, why did we begin this series with gradient descent? The answer is that a large chunk of work which we do in machine learning and deep learning is actually optimization. When we later dive deeper into several research papers on different kind of topics and models, we will see how much effort is being done by optimizing the models. But first, let's continue with the basics. As a quick reminder, from the last episode, gradient descent is an iterative optimization algorithm which is used in order to find the minimums of a given function, and respectively, gradient ascent is an optimization algorithm to find the maximum of a given function. As you already can see, I've written down the gradient descent update formula once again so that we can remind ourselves of how it looks like. So how does gradient descent works again? To summarize, we choose a random point on our function at a starting point x0, for example. Let's call it like this. And from there on, we can iteratively update our x value such that we can get closer, or we try to get an approximate value towards the real minimum value for x. So let's start implementing gradient descent in Python. I already written down the main function where we define our function, our well-known function from the first episode, x to the power 4 minus 2x squared. And I already implemented a class which will compute automatically for us the first and second derivative. So we don't have to do it ourselves. But in case you want to follow along, you can just write out or write a function which computes the first derivative and another function which computes the second derivative. Will also work fine. And then we define two arguments, x hat and alpha. Alpha is our step size, and x hat is the initial position from which on we want to iterate. And then we want to call gradient descent, give the function all the information it needs, and we have also a maximum iteration number. So we say after 1,000 iterations, this algorithm should stop. And what we want is to print out what is the converged x hat value, what is the first derivative, and what is the second derivative at our final x hat value. Okay, let's implement that. So how do we do it? We do a while loop, and of course we don't want to run it forever. So what we have to do is we have to keep track of the current iteration, and after each update we want to increment the value, not max iterations, current iteration, and if the current iteration is equal to the max iteration, we want to break out. And now comes our update rule. It's x hat equal to x hat minus alpha times the first derivative evaluated at x hat. Note that you can also write it in a more concise manner like this. I've just written it out so that it matches the update formula which we have seen from before. Okay, so in principle this should already work, but what we can also do is we can also store a previous value. Why? You might ask. The reason is that when our updated x hat value doesn't change from the previous value, then we can assume that we already found a solution or it converged to some point, and we can already stop from there and don't have to continue iterating. So what we have to check is if x hat pref is the same as x hat. If this is the case, we want to break out. And that's it. Basically, that's the gradient descent algorithm in a very simple form. Now let's execute it. And as you can see, nothing happens because we forgot our print statement. Here it is. So we want to print out to which value x hat converged, what's the first derivative, what's the second derivative. Let's execute it once again. And as you can see, our x hat value converged to a value of -1. The first derivative is approximately 0, and the second derivative is 8. And this is exactly what we calculated analytically or by hand in the first episode. What we can also do is we can round our values a little bit. We don't need to have all the decimal values. We can, oh, yeah, let's not write like this. Okay. So if we compute it again, as you can see, we are now rounding to 4 decimal places and not all of them. And as we can see, -1, approximately 0, and 8. Okay, this seems to be working and correct. So let's also maybe print out the current iteration in order to see if it really needed 1,000 iterations or if it stopped at some point. And as you can see, it really ran 1,000 iterations because it tries to converge as close as possible to -1. Didn't reach it quite yet. The updated values will be very small towards the end, but apparently it changes a little bit. Okay, so good so far. Let's do the same with gradient ascent. And for gradient ascent to work, we don't have a lot to do, because the only thing which changes is the sign. And in a concise notation, we must also change the sign, and that's basically it. What we changed though is where we start. We start at 0.2, and alpha is the same. So if we now execute our gradient ascent method, what happens? Okay, as you can see, our x hat value converged to approximately 0. Our first derivative is approximately 0, and the second derivative is -4. This is also what we computed in the first episode. You might ask what happens if we increase the maximum iterations. Let's put it to 10,000. This needs a little bit. Yeah, so as you can see, the computation takes longer, but as you can also see, the value is now more accurate. We now have 0.000, and before we had 0.0037. First derivative is also approximately 0 and derivative -4. So as you can see, the longer we iterate, the more precise our value will get. Okay. I've also prepared some scenarios which we will have to take a look at, and I see you there. So let's start with our scenarios. So this is the first one. As usual, we have our already well-known function from before, and also with the same arguments: x at -1.5, alpha 0.001, and maximum iterations of 1,000. And I want to show you an animation which demonstrates how gradient descent works. And these are the updated values are displayed by x hat, and x hat are the red dots on the function. And when I click on play, you will see how with each step the updated value gets closer and closer towards the minimum. And we could also observe that the initial steps are bigger due to the higher negative slope, and afterwards, as when we approach our minima, it will get smaller and smaller. In the second scenario, I want to show you the same but with gradient ascent. So we have here x hat -0.7, alpha the same as before, maximum iteration the same before, the function the same as before. And now as we can see, it's slowly going upwards towards the maximum, as we would expect when doing gradient ascent. As you can also see, it takes some time, a few iterations until it gets there. But at some point, it will get closer and closer, and if we increase the number of iterations, it will get more and more precise, or more and more closer to the maximum value, which is at x equal to 0. Okay. So let's also see where gradient descent can also go wrong. For example, now we choose a different starting point at minus 1.1. And now, as we can see, what happens? Of course, gradient descent follows the slope in the upwards direction. But what happens is our function is approaching infinity as x goes to minus infinity. So gradient ascent will never converge in this case. So we have to watch out and care what kind of initial starting position we take. So it can make a difference depending on the function. Let's go to the next scenario. In this case, I want you to demonstrate, for example, that depending on the starting position, in this case x hat equal to 0.2, that we are approaching the minima at 1, but we are not reaching the minima at minus 1. But in this case, it's not really being wrong, because it still finds a minima. We will see another case where it really goes wrong. And this is the case with this function. This function looks a little bit funky, but what happens in this case is, when you notice, for example, we want to maybe reach this minima at 0.15, it's approximately at this value, but we also have a plateau, which is not a real minima, at x equal to 2. And what happens is that our updated value gets trapped by this plateau, because at some point the derivative of our function will be very close to 0, and our updates will eventually stop at some point. And that's a behavior we, for example, don't want in this case. But this could also happen. Or the next scenario, we might have a function where we have minimas at different kind of levels. So for example, let's say we want to reach again this minimum here, but we also have a minimum further upwards here. And what can happen with gradient descent is that we again converge towards a minima at x equal to 1, but we will never reach the minima at the lower value here. And another scenario, the other scenarios showed us quite clearly what happens to the updated value when the slope, for example, changes, or when the function has multiple minimas and so on, or is unbounded towards one direction. But we can also go wrong when choosing a wrong step size parameter. Or, for example, in this case, we have another function. In this case, we want to have a look at x squared, and we are starting at minus 1. And now we have chosen as a step size 10 to the power of minus 5. With so 0.00001. And as we have an iteration number of 10,000, so a lot of iterations. And what happens is, when we choose our step size parameter so small, you don't even see how this updated value, how this update is even happening, because the step size parameter is so small. We would have to wait a million maybe a million iterations until we really reach our minimum point. So it's not good to choose a too small step size. But we can also choose the step size too large. For example, we have the same function again, x squared. And for example, we are starting at x hat minus 1. And we have a step size parameter of which is greater than 1. A little bit greater than 1. And let's see what happens in this case. As you can see, the updated value is jumping upwards. It's jumping from the left side to the right side and back, and it's going upwards. Why does it happen? Because it's kind of an amplification process. We are jumping from the left side too far towards the right side. Then we are at the right side, we jump too far to the left side, and so on. And this amplifies and our x, and we will never converge actually and never reach our minimum. I hope this scenarios gave you a deeper insight into how gradient descent and ascent works. It is crucial to understand this optimization technique in order to understand error-based learning. Don't worry if error-based learning doesn't ring a bell. We will learn in the upcoming episodes what error-based learning actually is and what other learning techniques in machine learning exist. But before diving into the process of learning and training models, we will talk in the next episode about data, information, and what is knowledge. And afterwards, then we will start with error-based learning, where we will see gradient descent in action. So thank you for joining this episode. See you in the next one.